Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course. And as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on side as we jump into the Chapter 6 Test and Cumulative Assessment in the Big Ideas Math Integrated Math 3 textbook. Rational Functions is the chapter, Cumulative Assessment, everything leading up to this from 1 through 6. We'll see what we remember how to do, when to do it. 1 through 14, I think, in the chapter test, and 1 through 8 in the cumulative assessment. Check the description section down below for the PDFs of each individual one. I'm sure we're going to have to do some graphs, so if you need to download some graph paper and print it out, go ahead and do that as well as timestamps for each individual problem. As you know, for these parts, this is at the end of the chapter. Less teaching, more doing. So, if it's something we've done before, I'm just going to dive right into it. Let's just get these problems taken care of. Without further ado, let's go ahead and get started. We have numbers 1 through 3, which say the variables x and y vary inversely. Use the given values to write an equation relating x and y. Then find y when x equals 4. These would have been out of section 6.1. This is inverse variation. That is literally what the section was called itself. So number 1, x equals 5, y equals 2. The equation is y equals a over x. So we're doing that. Using that to solve for a, our constant of variation, so we can write our equation as 10 over x. Y equals 10 over x, and now we can find y based on any x that they want. They say when x equals 4. 10 over 4 also reduces to 5 over 2. You could also write 2.5, but 5 over 2 shall do. Number 2, these problems are all the same when it comes to what we do. It's just how they provide them, and these look like they have a few more fractions. So x equals negative 4, and y equals 7 halves. We have y equals a over x. Looks like a proportion to me, something where I guess if I multiply both sides just by negative 4, I'm taken care of as well though. So negative 4 divided by 2 is negative 2. Negative 2 times 7 is negative 14. That is our a value of negative 14. So we can then write our equation of y equals negative 14 over x. This is our inverse variation this time. We use that by substituting now negative 4, what are we substituting? 4. Substitute 4 in for x. And we get negative 14 over 4 is negative 7 over 2, which is negative 3.5. But we write what we write, right? All right, number 3, two fractions. We have y equals, x equals 3/4, y equals 5/8. We have y equals a over x, so 5/8 equals a divided by 3/4. Now I brought this stuff up in the chapter review as well. We could rewrite this as like dividing by 3/4 is multiplying by 4/3. So I could rewrite it as something like 4a over 3. It's kind of cool, right? We could cross multiply, have some fun with that. Why don't we do that for a problem? It's up to how you want to present it. You can divide both sides by 3/4, which is 0.75. You can go in decimal form. I'm going to go a little more traditional. 15 equals 32a, so a is, 15 over 32, and I don't believe that thing reduces. So a is 15 over 32. Now, when you write it as a over x, we don't write 15 over 32 over x. We don't do complex fractions as a whole. That 32 multiplies with x in the denominator. So this is 15 over 32x, like 32x. X is still varying inversely. It's still in the denominator like that, but that's how we write it. Now we got to substitute 4 for x. So 15 over 32 times 4. These don't reduce at all with the 15. So 32 times 4 straight up is going to be 128. 15 over 128. And yeah, if they couldn't reduce before, they still can't reduce now. Don't be writing decimals for those guys. That should be good enough. That is it. So inverse variation questions are done there, unless they do some word problems later, because these are mixed review, right? Just because this was the first section doesn't mean they don't bring it back later. All right, numbers 4, 5, and 6, they give you graphs, and they say the graph shows the function y equals 1 over x minus h plus k. It's not even in any a, it's literally a equals 1. So what are they saying? Make the equation. Determine whether the value of each constant h and k is positive, negative, or 0. Explain your reasoning. These are just about the asymptotes, guys. So each explanation will be, what are my asymptotes? Are they positive, negative? The vertical asymptote is our x equals h. This is x equals negative 4, and this is y equals negative 2. So in terms of, I'm going to write as much as I can here. Vertical asymptote, x equals negative 4, horizontal asymptote, y equals negative 2. this is our k value, this is our h value. So h is negative, less than 0, and k is less than 0. That's how I'm going to say them. H is less than 0, k is less than 0 based on the graph. Your equation for this, given that we know a is 1, is going to be, just because I can do this, y equals 1 over, now x minus negative 4 is x plus 4. That's what we'd actually write here. And then plus k is minus 2 like that. That's the equation itself. But h is negative, k is negative because of those things. Kind of interesting questions. That's why I'm going to make the equations out of them, because we're not graphing. We're not graphing, so we're very limited in what we do. It's just based off whether the asymptotes are positive or negative if you want the true answers. For example, number 5. And by the way I'm drawing the asymptotes is by clearly showing what lines these curves are approaching. They're approaching this line here and this line here. My vertical asymptote is positive, so h is positive. My horizontal asymptote is positive, so k is positive. I mean, those are the answers if you want them. H is greater than 0, k is greater than 0. As far as equations go, this is h equals 4 and k equals 2. So this is going to be y equals 1 over x minus 4 and plus 2. It's actually the same equation as the previous one. And remember, these are ones. These are ones here, by the way. They mentioned that themselves. But this is the same, except instead of negative 4, negative 2, it's positive 4 and positive 2. Number 6. Let's get that graph copied and pasted over. On number 6, we have, well, the k value, hold on, the h value is here, it's a negative, it's negative 2. The k value is 0. What were our options? Positive, negative, or 0. So our h value is negative, being less than 0. Our k value equals 0. It's all about, once again, the asymptotes. As far as an equation goes here, this would be y equals 1 over, and it would be x plus 2, and plus 0, which you don't need to write. So when it comes to graphs, if you need to figure out what to do, we actually start from our asymptotes, and then we use the a value as needed. All right, numbers 7 through 10 say perform the indicated operation. We have division, subtraction, multiplication, and addition, anything stemming from sections 6.3 and 6.4. So get ready for anything we got to do. Beginning with division. Okay, with this problem here, what I'm actually going to do before the multiply by the reciprocal is simplify what I can on these own fractions. 6 over 2 is 3. Y squared, remove both of those to remove 2 y's from down there, and we have just 3 over xy like that. On here, 3 over 4 can't reduce. Remove both x's from here and 2 x's from there. Remove a y from up top and one of the y's from the bottom to get y to the 4th. Now, the reason I'm not doing anything from this to this or this to that, number 1, it doesn't seem like I can. Number 2, it's still division. It's not multiplication yet. So what I have to do is rewrite this as, well, what this appears as, 4xy to the 4th. But now we multiply by the reciprocal. So this is xy over 3 like that. Now I can look to do some more things, like, for instance, 3 over 3, x over x, and this y, and remove a y from there. Now, you can say everything canceled on top and nothing's there. A common thing that people tend to do, they don't write 0. When people cancel everything on top, they tend to just write this on top. Don't do that. There's still a 1 on top. So this is 1 over, and we have, I guess, 4y cubed. 1 over 4y cubed, and that would be our final result there. So 1 over 4y cubed after everything's cleaned up. I know I clean up things differently than others, and you might be confused in where I do the crossing out. I can mostly follow my work and see what's still there, so hopefully you can as well. As far as restrictions go, there were x's in the original, whether down here or right here at the time, that don't exist in the other thing. They couldn't equal 0 before, so we have to mention even still that they can't equal 0 now. Y can't equal 0, but it is implied from what we can still see in that equation. Number 8's a subtraction question. Completely different from the division question when it comes to what to do. We have to find a common denominator from this one. So we will begin by factoring. We'll begin by factoring this guy right here. This denominator factors into x plus 4 times x minus 3. This also has an x plus 4, which means it's missing an x minus 3. Not a plus. So we got to multiply top and bottom by x minus 3. And boom, we have a common denominator. So we need that denominator. This is not an equation. It is an expression. I say that because of what we have to do when solving equations. We tend to get rid of the denominator. That is not the case here. 3x is going to be subtract, we do -6, distribute the negative, -6 times x, -6 times -3. So minus 6x plus 18. And we combine like terms, and we now have -3x plus 18 over x plus 4 times x minus 3. Now this could be the correct answer, and it actually is probably fine. What I am going to do, however, is factor a -3 out. There's a possibility, doesn't seem to be the case here, there's a possibility that what you factor can lead to cancellation here. Like if this was x minus 3 right here, they would go away. But it's not. It's x minus 6. So we'll leave it like that, as simplified as we can get, I suppose. X can't equal -4 and 3, but that was true from the original problem, so we don't need to list other exclusions. There were no other exclusions on that problem. Number 9 is a multiplication problem. It's like the division, only there's no flipping to be had. So we write it straight up as it is, and we do some things on it. Now, the book tends to merge these all as a single fraction. In this particular problem, I don't mind doing that. It's kind of there, set up to go. One big fraction over another, excuse me. This factors into x minus 4 times x plus 1 and x minus 6. All on top divided by all on bottom. This is x minus 6 times x plus 3 times x plus 1. Some things go away. Couple x minus 6's, couple x plus 1's. You're left with x minus 4 over x plus 3. And that is the simplified version. No, you can't cancel out these x's. No, I will not allow you. There are restrictions, the ones that we can't see anymore. X couldn't equal 6. X couldn't equal -1. So -1 and 6 are our restrictions on that. Number 10, last of these kinds of problems, we have addition. Maybe the most basic. We'll see. Actually, that multiplication one wasn't bad. Number 10. X squared minus 25 is the difference of two squares, which factors into x minus 5 times x plus 5, which means this guy's missing an x minus 5 that can multiply on top and bottom like so. Now we have a common denominator. That's our goal. 4 distributes into x minus 5 to get 4x minus 20. We add the 2x with it because now it's all over a common denominator of x minus 5 times x plus 5. Leave those factored on bottom. On top, our goal is to combine. 4x plus 2x is 6x. And even still, despite the fact that we can get a common factor of 2, they still refrain from ever canceling out anything on top and bottom from an addition or subtraction problem that needed a common denominator. I was really hoping for it sometime on the chapter test. Maybe, just maybe, the cumulative assessment will show it, but no. The lecture portion of section 6.4 did have it, but they never did it again. You won't know what they look like. There are no restrictions to list, by the way, besides what you already see. You won't know what they look like unless you actually play with them a lot. So I don't know. They're hard problems to write, but they're possible to make. Number 11, let g of x equal x plus 3 times x minus 2 all over x plus 3. They say simplify g of x and determine whether the graph of f of x minus 2 and the graph of g are different. Explain your reasoning. Here's the thing. These two divide out, right? They cancel, and you're left with x minus 2. So now you have suddenly g of x equals x minus 2. But this is where those exclusions apply, the restrictions. X can't equal -3 here. Whereas you have an f of x equation that's just literally f of x equals x minus 2. So you're saying, what's the difference between the two? Well, the difference is, in this one, x can't equal -3. And in this one, x can equal -3. So the graphs are the same with the exception of at x equals -3. And I know we didn't do these in our graphs. This chapter didn't seem to feature them. I guess wait till pre-calc. G and f are the same graph, like y equals x minus 2. That's a slope of 1 and y-intercept of 2. They're linear equations. Are the same graphs for every value of x except where x equals -3. At x equals at f of -3, sorry, at f of -3, you have -3 minus 2 is -5. At g of negative 3, there is no defined value. Now, to the left and right of it, you do have defined values. Therefore, there is a limit as x approaches negative 3 on g where you have what's called a hole. We approach negative 5. So these graphs, you know, they're both this same kind of graph like this. Actually, let me actually get the graph paper for it. This is a teaching moment for something even for pre-calc in the future. Just make a tiny graph here. This is y equals x minus 2. That means you have a y-intercept of 2 and a slope of 1. So these graphs look like, you know, this, like that, and then downward as well. So here's our graph, right? Our graph looks like this, y equals x minus 2, which is great. Now, at negative 3, wait a second, I must have messed something up. Oh, x minus 2. Okay. At negative 3 for f, you would have this point, negative 5. Boom. The g equation is a little different, though. For g, you don't have a value there. Instead, you actually just have this big gaping hole. It's not big, but just you would draw an open circle on that point right there. To say it jumps it, normally I wouldn't actually have the blue thing go through it like that. I would just build a hole and go from there. You have a hole there. So it's the same graph except that. So they are almost the same, but there's one slight difference. Anyway, I want to spend some time on that problem just to mention what we're talking about, but no defined value when x is negative 3 for g. All right, number 12. You start a small beekeeping business. Why? Your initial costs are $500 for equipment and bees. You estimate it'll cost $1.25 per pound to collect, clean, bottle, and label the honey. How many pounds of honey must you produce before your average cost per pound is $1.79? Justify your answer. So our average cost I'll put as C. H is, let's see, P is the amount of pounds of honey we'll have. So if my cost for all of this will be $1.25 per pound of honey times the number of pounds of honey plus the $500 upfront cost. But my average cost needs to divide by the number of pounds of honey to get an average cost per pound. So this is our equation we need to set up. They say, how many pounds of honey must you produce before your average cost is $1.79? So you have two options here. One of them is substituting $1.79 right now, like this, and solving for P. So to do this, we'll multiply both sides by P. We'll subtract 1.25 from both sides, and that's, I think, 0.54. And we'll divide both sides by 0.54, and we'll get some value for P. Let me use the calculator for that. 500 divided by 0.54. I'm getting a P value of, it's kind of a weird decimal, but I'm getting 925.9259. So 925.93 about pounds. I'll say 926 pounds. I'll just round it. 926 pounds. So 926 pounds of honey gets you down to that average cost of $1.79 per pound. Now, that's one way to do the problem, is by substituting first and then solving. What we've also seen was kind of finding the inverse, solve for P, and there are two different ways to do it. I'm going to do it the method that I've done a little more so, which you'll kind of see you get to the same version of the answer. But version I do more so is I multiply both sides by P, and I have two different terms with P. So I'd like to get them both, subtract 125 from both sides, get them both on the same side of the equation, so I can then factor P out like that. And then divide both sides by C minus 1.25. So you got that there. Now we can substitute 1.79 in for C right there. So 500 over 1.79 minus 1.25, which is 500 over 0.54. And you get the exact same answer there. So whether you want to solve for P first and do it, or plug it in first and do it, I'd probably do this first one in blue to solve. 926 pounds is what gets you that average cost. All right, number 13. You can use a simple lever to lift a 300-pound rock. Like a rock. The force F in foot-pounds needed to lift the rock is inversely related, okay, inverse variation, word problem, inversely related to the distance d in feet from the pivot point of the lever. So F is inversely related with D, distance. That means you'll need more force the closer that you are to the pivot point. You'll need less force the further away you are. And that actually makes a lot of sense if you think about how these things work. To lift the rock, you need 60 pounds of force applied to a lever with a distance of 10 feet from the pivot point. So 60 pounds of force and 10 feet away. Therefore, we need A equals 600 foot-pounds here in order to make any of a force, no matter where we are distance-wise. We need that as an overall. So our equation will be F equals 600 over D. So here's an equation. It says what force is needed when you increase the distance to 15 feet from the pivot point. Justify your answer. So you would need less force, right? So now this case, you would need F equals 600 over 15, and 600 over 15 is 40. So you need 40 pounds of force from that distance there. You need less force the further away that you are. And again, hopefully, I don't know if that makes sense to you, that the closer you are, the more you have to do it, and the farther you are, you get more kind of on your side, weighing it down when you do that. So that, it makes sense to me as an answer. Okay, number 14, last one from the chapter test portion. 3 tennis balls fit tightly in a can as shown. Write an expression for the height. This sounds like chapter 1. Let me actually copy paste the tennis ball thing. We might need to use it. All right, here's an image. Write an expression for the height of the can in terms of its radius r, then rewrite the formula for the volume of a cylinder in terms of r only. And then find the percent of the can's volume that is not occupied by tennis balls. This sounds more like chapter 1. This should be in the cumulative assessment portion. Anyway, the height of this thing, write an expression for the height in terms of its radius r. The height is basically 3 tennis balls, right? The 3 tennis balls have a radius here, here, another 2r here, and another 2r here. So the height is 6r, right? There's 6 radii stacked on top of each other there. The volume of the cylinder, a volume of a cylinder is pi r squared times height. So when we substitute 6r for height, they said in terms of r only, volume is pi r squared times 6r. So that'll be 6 pi r cubed. So volume is 6 pi r cubed, like so. That is part A. Part B says find the percent of the can's volume that is not occupied by tennis balls. So the volume of the can, I'm just going to substitute, wait. We're not substituting anything for R. The volume of the can is this guy, minus the volume of the balls will get us the total, the volume of the space. I'll just put space, the empty space. So V space equals 6 pi r cubed minus, now there are 3 tennis balls there. There are 3, the volume of a sphere is 4/3 pi r cubed. 4/3 pi r cubed. Oh, this will clean up a little bit. Take a look at this. 3 over 3 is 1. So now you have 6 pi r cubed minus 4 pi r cubed, which is 2 pi r cubed. So that is the volume of this. They said they'll find the percent that's not occupied by balls. So the percentage is going to occupy the space volume by the total volume, by the volume of the can. So that is 2 pi r cubed over 6 pi r cubed. And pi r cubes, well, this probably relates to us, cancels, and 2 6 reduces to 1/3. So the percentage is 33.3 repeating percent. It's 0.3 repeating, so 33.3 repeating percent for that one. All right, a little bit different kind of question. That feels a lot more like chapter 1, but we have it there. All right, guys, I'm going to move forward into the cumulative assessment. So this is anything from chapters 1 to 6. I have to think back. I've done a couple IM1 video recordings, so I have to think back about what our previous chapters were. I might even go like, oh, I don't know what chapter it's from, or like, oh yeah, how do you do that? We'll see. We'll see based off what they do, because they can ask tricky questions here. It all depends. Let's go ahead and see what this looks like. Number 1 says, which of the following functions are shown in the graph? Select all that apply. Justify your answers. all that apply? Oh, because they have different forms. Honestly, I don't remember the chapter this is from, so I can't help you there. Let's look at these one at a time. As far as A goes, y equals negative 2x squared plus 12x plus 12x minus 10. One way that I could know it could be the same. The A value being negative and this graph being upside down means there's a chance. What I really want to look for is the vertex. Now, out of standard form, you have a couple ways to get vertex. I'm going to use the negative b over 2a approach. X is negative b over 2a, which is negative 12 over negative 4 or positive 3. Before I keep moving forward, is the x value positive 3 for this vertex? Yes. In fact, let's write this vertex. It's at 3, 8. Let's see if we get 3, 8 for this thing. We have to substitute 3 for x now into this equation and get negative 2 times 3 squared plus 12 times 3 minus 10. By the way, I can't see this. Negative 10 is the y-intercept. I can't see the y-intercept of this graph, but it looks like it could go to negative 10. I'm a firm believer that this answer will be true. So this is negative 2 times 9, which is negative 18, plus 36, which is positive 18, and 18 minus 10 is 8. So yes, this has a vertex of 3, 8, which checks out. That means that A is indeed, A is a real one. A works out. B, I don't have to do quite as much work for several reasons. The A value's all wrong, being a positive 1. This one's, upward instead of downward facing, what have you. 13 is the y-intercept. I don't think so. It's not going to be B. C is very much so in play. In fact, C is the answer, the vertex of this guy. So I don't have to write any work for B. We know it's not B. C, I don't really have to do any work. I just want to call out the fact that your A value is indeed negative 2, same stretch factor. So same stretch factor as the first one, which means if this one works, then that being the same stretch factor is good. And this thing has a vertex at 3, 8 because this is in vertex form. This is x minus h squared plus k, so that's also good. So C is correct. D is close. The thing that makes it wrong is the A value, but this has an x-intercept. I'm going to call these things out. D has an x-intercept of 1 and a y, it has two x-intercepts, an x-intercept of 1 and 5. This graph has an x-intercept of 1 and 5. Does that make them the same? Well, you'd have to see if the vertex is the same. Now, the vertex has an x value of 3, but the y value, if you plug it in, won't end up being 8. The main reason I know that is because this A value is negative 1, and the other A values that are correct are negative 2. This is negative 2, this is negative 2. This one probably gets a vertex at 3, 4, half the size, and then it does this graph right here. So D is close, but D ain't it. So this is wrong, despite the fact that the 1 and 5 were correct. So the only answers here are A and C, not D and not B. So let me kind of write that in full here. A and C. Okay. Number 2. You step onto an escalator and begin descending. After riding for 12 feet, you realize you dropped your keys on the upper floor and walk back up the escalator to receive them. The total time T, this seems like chapter 6, the total time T of your trip down and up the escalator is given by T equals 12 over S plus 12 over W minus S. T is the total time, S is the speed of the escalator, and W is your walking speed. So because you begin descending downward here, I guess you're not moving, you're not walking, whereas here you end up walking up the escalator that's going down, so your speed has to beat that speed. Like if you walk 3 miles an hour and the speed is 2 miles an hour, your net speed is 1 mile an hour. You know what I mean? That's why they're subtracting those. So that makes sense. And 12 feet is part of the thing there. Okay, anyway, good question. We're not done, but good setup. The trip took 9 seconds and you walk at a speed of 6 feet per second. Find 2 possible speeds of the escalator. The trip took 9 seconds and you walk at 6 feet per second. So we're going to solve for S. I'm guessing ultimately this becomes a quadratic. So this is our setup. These are S's, not 5s. So we're going to solve for S here. In order to do this best, I suppose we should work toward a common denominator. Now, I have a personal thing behind having having a negative variable leading terms here, and it would be a leading term if you rewrote that. So here's what I'm going to do, guys. I'm going to turn this into the opposite of S minus 6, and I'm going to bring that negative up for the 12, or for the fraction, which means I'm going to subtract this over s minus 6. I personally prefer doing this. This might help me in solving the quadratic in general. So this plus turned into a minus given that I swapped this bottom. I hope that's all right. We didn't get to play with that very much in the actual section that we had. I got to multiply this by s over s, and this by s minus 6 over s minus 6. Now, if you'd like, you can either get a common denominator here or leave this as such so you have more of a proportion format. I'm going to go with the proportion format just because, well, hey, I can. So I'm going to have 9 equals, and I can distribute 12s minus 72, and here's a minus 12s, and then this is all divided by s times s minus 6. You know what? I'm going to go and distribute this one, s squared minus 6s, because eventually I got to solve for s anyway. So I'm going to multiply that. So I'm going to do two things at once. 12s minus 12s actually cancels. Those are gone. And I can now multiply both sides by s squared minus 6s. And then here, boom, I have 9 times s squared minus 6s equals negative 72. Instead of distributing the 9, I'm going to divide both sides by 9 and get s squared minus 6s equals negative 8. And now I can add that 8 over. Kind of confusing looking information, but we still have it. Plus 8 equals 0. And now we have s minus 4 times s minus 2 equals 0. So s can either equal 4 or 2, which means the speed of the escalator can either be 4 feet per second or 2 feet per second. Now, let's talk about whether there are extraneous solutions. This had a 6 minus s, and 6 minus 4 and 6 minus 2 are not 0, and 4 and 2 are not 0. So neither of these are extraneous, both of these work. Let's talk about why these should work. When we have this slower speed right here, 2 feet per second, you don't go down the escalator as much as an overall, right? You spend 9 seconds total on the escalator, it looks like. 9 seconds in total. And there's probably more time going down, I guess more time going down because you can walk faster to counteract that and get back up the 12 feet that you went down there, right? You'd spend 6 seconds, basically you spend 6 seconds going down and the other 3 seconds going up. You go back up 4 feet per second over that time to get there. Whereas if the escalator goes down faster, you're wondering, wait, how do you get back up at the same time? Because when you go down 4 feet per second, you take 3 seconds to get down to 12 feet. And then you go back up 6 feet per second. That takes you 6 seconds to do. So it's 3 seconds down, 6 seconds up. 9 seconds total there. So both seem to work nice on the quadratic to do so. Okay. I know I'm spending more time on these ones, but they're nice problems. Number 3. The graph of a rational function, chapter 6. The graph of a rational function has asymptotes that intersect at the point 4, 3. Choose the correct values to complete the equation of the function, then graph the function. Okay, this one here is kind of interesting because you don't really want to guess and check. You know, there are, let's see how I say this. There are versions of this problem. Excuse me. There are ways that you can do this problem where you can plug things in and have to do that division thing until you get that h and k right. But this form can also get us into that way as long as we get it right. It says choose the correct values. It means to me there's only one answer, not open-ended. Now your asymptotes intersect at 4, 3. That means your actual asymptotes are a vertical asymptote at x equals 4 and a horizontal asymptote at y equals 3. Let's actually start with the horizontal asymptote y equals 3. That means in this form, when you have x to the first power in both, these have to divide to get 3. Which of these options allows you to divide to get 3? Negative 12 over negative 6 would get you, excuse me, that won't get you 3, that'll get you 2. Which ones divide to get 3? 9 over 3. And that might be it. Negative 6 over negative 3 is 2 and 2 and 4. This might be the only one. So I believe these have to be 9x here and 3x there. Now we need to figure out, I'll just call this a b. I need to make 3x plus b to equal 4 because I need this to be the value for which, you know, you end up dividing by 4. So I have to solve for b. Wait. Based on x equals 4. So 3 times, wait, hold on. What am I thinking of here? what do I need to do? I'm sorry, I need this to equal, not 4, this equals 0 based on that being 3. Right? What am I thinking? What am I doing? Hold on. I'm overthinking this or underthinking this or whatever. When I substitute, okay, here it is. When I substitute 4 for x, I get 0 there. So 3 times 4, there we go. 3 times 4 plus b, I'm like, why do I have 2 variables? 3 times 4 plus b equals 0. There it is. 12 plus b equals 0, so b equals negative 12. So that's the b value that needs to go there. And this is negative 12 like that. So these are the values that would fit in here to get those bits. So negative 12, and that's one of our values, and 9 and 3. And I had to kind of pick and choose from there to get those first ones. So they said graph the function. So let's now kind of confirm everything that we did by doing division and getting into that other form. I think that's going to work best for us here. So let's do 9x plus 6 divided by 3x minus 12. 3x goes into 9x 3 times. Let me change the color on this. Goes into it 3 times, and we now have, when multiplying, that's 9x minus 36, and 6 minus negative 36 is 42. So our equation ends up being rewritten as y equals 42 over 3x minus 12, and this is plus 3. 3 is the quotient. Now, a couple things I can still do here, by the way. 3 is a common factor on bottom. So as a common factor on bottom, I can factor 3 out and get the x minus 4, which really helps in 2 ways. 42 divided by 3 is 14, and this gets us in that proper graphing form. So being 14, that is now our a value. It's not only smaller, but it is the a value. And there's the equation. Does this equation seem to agree that the vertical asymptote is 4? Yes. And the horizontal asymptote is 3? Yes. And they said graph it. And graphing is based off using that a value with these 2 asymptotes. I'll keep the scale normal. I think I can bother with doing that here. Let me just try and fit this all right there. So a vertical asymptote at x equals 4. Let me kind of change this up. Dotted line thinner. Vertical asymptote at x equals 4. Horizontal asymptote at y equals 3. They still have arrows. I hope that's okay. And 14. 14 can't divide by very many good numbers. 14 over 1 is 14. 14 over 2 is 7. 14 over 7 is 2. So I'm going to kind of just get those points in there. And I'll get a few more on the other side, I suppose. Let's go a little bit sharper on that thing. I believe it should go sharper. Now, let me get your y and x intercepts for you. That's based off the original equation a little more so. The x-intercept, where you set y equal to 0, 9x plus 6 equals 0. So 9x is negative 6, so x is negative 6 ninths, or negative 2/3. So negative 2/3 is our x-intercept. That's a point that I can plot right here, negative 2/3. And the y-intercept should be pretty close to that as well. We divide 6 by negative 12, and we get negative 1/2. Y is negative 1/2 is a point as well. So these are points that will be kind of on that graph. Let's also go 1 left and 14 down, which is about right there. 2 left and 7 down. We have those points. 7 left and 2 down, and 14 left and 1 down. So I get a lot more points on this one to show that graph. So a lot to do on that problem. This cumulative assessment taking up some of our sweet time. The other part I was really bothered with here was just that silly, this part here. I had to plug in 4 to find the b. Okay. Is that it? Is that it? That's a lot. Choose the correct values to complete, then graph the function. Okay. Okay, let's go to number 4. The tables below give the amounts A in dollars of money in 2 different bank accounts after T years. I might have to copy paste these. Determine the type of function represented by the data in each table. Okay. You might, I don't know how big or small those numbers are for you. Let's bring them here. They might still be pretty small here. Apologies. Okay. Determine the type of function. This one has a linear increase as t increases by 1, adding 1 each time. And that's going to be the same for this one, of course, as well, right? As t adds 1 to each of these, what's happening with A? The amount over time. This one is adding, it looks like 110. So that's linear. So the first one is linear. Explain your reasoning. It's a constant increase on y. Constant increase on y. Normally I'd say a lot more. As x increases by 1, y increases by a constant amount. This one here is not linear. We add 100, then we add 102, and then we add 104.04. That's quite different. Now, what is that one? Well, you can do 5100 divided by 5000, and you're going to see it's the same thing as 5202 divided by 5100, etc. This is an exponential function. If it wasn't, we'd be running into some trouble here, especially with the decimals. But 5100 divided by 5000 is this number 1.02. Now, if you notice, 5100 times 1.02 gives us 5202, and that number times 1.02 should be the 5306.04. So we are multiplying by 1.02 each time, and because we're doing that, that makes this an exponential function. So times 1.02 times 1.02, etc. It's an exponential function this time. Now, we're not talking geometric sequences, so to speak, but I can still say the phrase common ratio. Common ratio for y, common multiplier is also another way we can say that. Okay, so that's part A, determine which type for each. Part B says which account has a greater initial balance, explain your reasoning. Now, our initial balance here is $5,000. Our initial balance here we can't see. This would be year 0, but this would be, if you subtract, I said plus 1110 right here. Give me a second. That's just plus 110. I can subtract 110 from this set, and over here at year 0, let's write it over here. At year 0, we'd have 4890, I think. So for part B, the savings account has a greater initial value. There's not much to explain other than say what the values are. Initial value of 5,000, then the checking account, which you'd subtract the 110 to get 4890. I hope that calculation's right. It seems basic enough to be able to write, but I don't want to make a mistake on that. Part C, which account has a greater value after 10 years and 15 years? Justify your answers. What would be really nice is to come up with equations for both of these. So on the first one, the checking account, y sub checking, is going to be an increase of 110 every year. Oh, I'm sorry, they're using A, not Y. Account of checking is 110 per year times the number of years plus 4890. This is actually your y-intercept here. Keep that in mind. The other one is A sub checking. It's a C, not an S. What am I doing? A sub C, and this is A sub S equals, this is a y-intercept of 5,000. This is y equals AB to the x form. 5,000 times 1.02 to the t power. So these are the two equations we're going to be using for these sets here. So for 10 years, we have to compare these two. And we'll have A sub C is 110 times 10 plus 4890. And let's check that out. I'm getting $5,990. Whereas this one, on the savings account, you start with more, but maybe it has a slower increase over time. So we'll have to see if it actually has more than it or not. So after 10 years here, this is 5,000 times, I'm doing this in my calculator, by the way, 1.02 raised to the 10th power. And I'm getting more money here. So I think this is going to have more on both of them, but $6,094.97. So bigger. 15 years later, there's no reason why this exponential function won't still be eclipsing it, I think, at that point. Yeah. Maybe. This 110, I mean, it should be. It should still be more. But 110 is a smaller... Maybe not. We'll see. A sub C. Normally we talk about exponential functions dominating over time, but it started with more. So we'll have to see. 110 plus or times 15 plus 4890. 5,000 times. to the 15th power, excuse me, 15th power. All right, so let's do those ones again, but I substitute a 15 instead of a 10. So when I substitute 15 for the checking account, I'm getting $6,540. And then for this one here, the savings account, I substitute 15, and I get $6,729.34. 6729.34. So this still has more when you do that. So bigger. All right, let me pause for one moment here. Okay. I was just sitting around processing it, going like, why would they have both of these bigger over these times? I'm curious whether there's something messed up with the tables, but this is times 0 and that's time 1. So I think it is as it is. So I'm just going to, yeah, I'm just going to leave it like that. We're all good. All right. Number 5. Order the expressions from least to greatest, justify your answer. Okay, interesting. So 5 has a value of 5. Let's see. Let's bring these problems over and let's evaluate them. Because we can probably do rankings and stuff later as far as what's biggest, what's small. So this is 5. This is the cube root of 125, which is 5 squared, which is 25. So that's obviously bigger. 25 to the 1/2 is the square root of 25, which is 5. This is the square root of 25 squared, which is 25. This is the square root of 125 cubed. Now, that's a pretty big number. We'll talk about that one in a second. And this is the square root of 5 cubed. Now, the square root of 5 cubed is more, like this is 5 to the 3/2 power. That's more than 5. Keep that in mind. It's not quite 25, because that'd be 5 to the 4/2 power. This should probably be the, I guess, the biggest number. Let me think about that one. Square root of 125 is something more, yeah, it's something more than 10. Square root of 100 is 10. And 10 cubed is 1,000, so this will be more than it. So when it says order the expressions from least to greatest, you have kind of options here. I can say 5 is on the same level as 25 to the 1/2. So these are both the smallest ones. These are each less than our, I guess this one, the square root of 5 cubed, because that's somewhere between 5 and 25. This is without a calculator, by the way. And that is less than the ones that equal 25. So what equals 25 is, I need more room on this. What equals 25 on this one is, whatever, is, cube root of 125 squared and root 25 squared. And both of these are less than 125 to the 3/2 power. So that's how I'm going to indicate those, ranking them, because some of them are equal. It's kind of a weird thing to put there, but that's how I'm going to write it. Okay. That was the way that was written. Okay, here we go. Number 6. You claim it's possible to create a function from the given values that has an axis of symmetry at x equals 2. What's axis of symmetry? What? I guess that's quadratic function graphing. Your friend claims it's possible to create a function that has an axis of symmetry of x equals -2. What values can you use to support your claim? What values support your friend's claim? So I guess both work. Okay, so we have my claim and my friend's claim from these options. Let's kind of just bring this all over in case we need to write some things down. Now, axis of symmetry is all about that -b/2a. So these are our b and a values that we're referring to. So for my claim, my -b/2a needs to be 2. So I need to find 2 values that'll work with that. At the very least, let's multiply both sides by 2. So x, sorry, don't worry about the x. So -b/a, or how about this? b/a equals -4. Multiply both sides by that. So I need 2 numbers to divide to become -4. So I can do 8 divided by -2 to do that. that my only option? I can also do 12. No, I can do 8 divided by -2. Do I see another one? I don't think so. So I can make b equal 8 and a equal -2. Therefore, I'm going to have -2x squared plus 8x plus 8, and I think that should work for myself. That's my claim. For my friend's claim, I need their -b over 2a to equal -2. So when I multiply both sides by -2 there, my b over a is going to equal +4. So I need to support my friend's claim. To equal +4, I can do, there's no 8 over 2, there's -6. There's 12 over 3. So I can use that one. Does anything else work there? That might be it. So I can make their b become 12 and their a become 3. And that would give us that 4 set for the -b over 2a. So that would be 3x squared plus 12x plus 8 on that one. Okay, 2 more questions. Number 7. Can we beat the hour mark? I don't know. Choose the correct relationship among the variables in the table. Justify your answer by writing an equation that relates P, Q, and R. All right, A. Hold on, let's bring the table with this thing. Might not be able to finish in that hour mark. Okay. A. This is part of that current chapter. The variable P varies directly with the difference of Q and R. So for that one, oh, it says choose the correct relationship. I see what they're saying. These aren't different parts. These are different options. So P varies directly with the difference of Q and R. Let's see if that's the case. Let's try -12 equals... Actually, so let's do this. Let's get A by itself in that scenario, where we get A equals P over Q minus R. Let's see if this works on all of these here. P over Q minus R gives us -12 over Q minus R is 4. That's -3. Let's see if this works. 3 over 1 minus -10 is 1 plus 10, which is 11. That doesn't seem to work. Those aren't constant, so it doesn't look like the answer is A. Let's try out B. The variable R varies inversely with the difference of P and Q. So R varies inversely with the difference of P and Q. When I get A by itself, that would say A is R times P minus Q. So let's see if these are constant. When we do, and hopefully you can kind of see all these eventually. I'm going to keep bringing this table down. I hope you don't mind. Just kind of shift it down so we can take a look at it. A equals, let's do R times P minus Q. That's -12 minus 20 is -32. That's -512. Let's try this one. R times P minus Q. That's -10 times 2, which is -20. Those are not the same. So that's not the relationship. Just keep bringing it down as we keep doing more. Part C, or option C. The variable Q varies inversely with the sum of P and R. So varies inversely with the sum of P and R. So A would be Q times P plus R as a constant. Let's test that constant. So we're going to check A is Q 20 times P plus R. -12 plus 16 is 4. That's 80. And Q times P plus R, 3 minus 10 is -7. Those aren't the same. So hopefully I'm doing these right, meaning hopefully D is the answer based on these ones being wrong, because these are way wrong. I'm not even bothering checking anything after the first 2 tests. Not even close. Part D, we have the variable P varies directly with the sum of Q and R. It varies directly with the sum of Q and R. So A is P over Q plus R. Let's test that one out and see if we have constants in that one. So A would be P over, oh, here's the problem. These are fractions. Q plus R is 36. That's -1/3. Let's try the next one. P over q plus r. 1 minus 10 is negative 9. That's also negative 1/3, so that seems to work. This is probably right. So p 30 over q plus r, that's negative 90. That's also negative 1/3. And negative 1.5 p over q plus r, 4.5. That's also negative 1/3. So cool. So a is negative 1/3. And then they said, write an equation that relates p, q, and r. So this equation will be p equals negative 1/3 times the quantity q plus r. That is a direct variation on that one. And that would be our final. So D is the ticket. D is the answer, and then we have an equation based off that. All right, there's kind of a little bit to do. Last question, number 8. You have taken 5 quizzes in your history class, and your average score is 83 points. You think you can score 95 points on each remaining quiz. How many quizzes do you need to take to raise your average quiz score to 90 points? Justify your answer. This sounds like the last chapter. We had something with this, I think, in section 6.5 with these things. So we've taken 5 quizzes, and your average score is 83. We need, sometimes I have trouble with these. Sometimes I'm good with them, sometimes I have trouble. You think you can score 95 points in each remaining quiz. So let's say all of my quizzes so far, I've taken 5 quizzes. So my average is 83. So 83 times 5 is how much I've scored so far. That's 415. So 415 points I've scored so far. If I add an extra 95 points per quiz times the number of quizzes, and I divide that by basically what my total amount would have had to have been. Wait, hold on. I'm sorry. When I divide it by the total number of quizzes, I get an average. I need my average to be what? 90? So I've taken 5 quizzes so far, and I need to take X more quizzes on top of this. So this is what score I need in total. All my points so far, plus all of the points I need to make, divided by all the quizzes I've taken so far, plus all the quizzes I need to take. And this will equal average score of 90. So there's my initial setup on this one. Now let's go ahead and solve. How many quizzes do you need to take to raise your average score to 90? So let's multiply both sides by 5 plus x. I'm probably going to say x plus 5 there. And you get 415 plus 95x. Actually, I'm very OCD about this. 95x plus 415 equals, and distribute the 90, it's 90x plus 450. Subtract 90x from both sides. Subtract 415 from both sides and divide both sides by 5. You get x equals 7. Now, I'm not going to vouch for whether that's correct or not, like by plugging it in, but you can try it for yourself. You can do 7 more quizzes with an average of 95. Basically, do 95 times 7 plus 415 and divide it by 12. So 7 quizzes will get you up to that average score of 90 if you get 95 each time from what you have now. All right, guys, that's the end of that one. That'll do it for this one. We did get under the hour. This is Mr. Robinson. Thank you so much for watching. Some of those were clever and different. Not every kind of problem under the sun was hit from all the reviews that I wanted to do, which is just too bad, but hopefully you got some good stuff learned along the way. We're going to go to Chapter 7 next. So, guys, thank you so much. Take care. I'm going to see you in that next one.